Hello, my name is Aron Heleodoro, and today I'm gonna talk to you about my trajectory to get a job in Asia, and also a little bit about my research. I'm originally from Brazil. I started my undergrad there studying physics. I spent 2 years in Brazil, and then I moved to France to do a double diploma program where I studied engineering and physics for 3 more years. While in France, I had the chance to take lots of interesting abstract math classes, and at some point, it dawned on me that what I really wanted was to do math research. So at that point, I still had a lot of background to catch up in maths. So I spent 6 months back in Brazil, and then I went to the US, where I got my PhD after 6 years. So I got into this area of derived algebraic geometry and applications of it, which I'm going to talk to you a little bit more later. But after that, I applied for jobs when I finished my PhD, so through math jobs. And I first got a postdoc at the University of Illinois in Urbana-Champaign, where I worked for 3 years. And then after that, I got a second postdoc, this time around in Hong Kong, at the Chinese University of Hong Kong, where I was for 2 years. And now I'm in a third postdoc, also in Hong Kong, now at the Hong Kong University. Maybe just more specifically, how did I get to China and Hong Kong? Well, actually, it was sort of a similar process as how I got my previous postdoc in the US. So I did usual application through this website, Math Jobs, where you get posts from all over the place. Maybe it's worth saying a couple of things about how job applications went for me and how I managed to succeed a couple of times. So one thing you have to do is to reach out to people, and it doesn't even matter if they're a little bit far from their area. You want to engage with them and let them know what you're thinking about, so that they can consider you when they're making their hiring decisions. Then the third aspect is the interview. So different places do this in slightly different ways. In the US, for my previous postdoc, I wasn't invited to give a talk before the job offer, but once I was offered the job, then I went and I gave a talk. Here in Hong Kong was the other way around. They first invited me to give a talk, and after that, they offered me the job. And the thing to be aware, I guess, is that sometimes even a simple talk invitation could mean that they're considering you for some post. And they might not say that explicitly to you, but it's a good thing to have. I think for tenure track jobs, they're a bit more direct about this. The fourth point, which is very important, is to follow up. Even if you don't hear back, a lot of professors serving on those hiring committees can be very busy. And sometimes they still haven't filled a position. And if you reach out, maybe you can get something. So if you give a talk and you get a sense that people like you, or at some point you got an email or someone asking a bit more about, like, oh, if we were to offer you a position in this place or something, but then they never get back to you, it's follow up. And I guess the last thing, it's also a bit goes without saying, especially in the last years with how hard it was with the pandemic and less jobs being available, which I think are starting to pick up now, is you have to apply essentially everywhere. It's I think unless you're really at the top of your field, there's not that many. You don't get many choices, but you can still find some positions, and good positions if you have a combination of different things. And I mean, sometimes it's hard and you still don't get an offer. But the point is, in academia, you do have to be open to going to different places. And I guess this was one of the things that happened to me. I was open to come here to Hong Kong, and I've so far been enjoying it a lot. The academic environment has been great. I had great mentors, and my research is going really well. And now I want to tell you a little bit about what are my research interests. So I'll say that my research falls into two different areas. One is called derived algebraic geometry, and the other is called geometric representation theory. Both of those areas have a lot of background to start, and even to talk about what are the main problems. So I decided to do a presentation where I go through these words. We put three words together in both of those. So I want to try to explain what each one of those words are, sort of starting from the right and going to the left, and then while doing that, giving an idea of what it is that we study in those areas. So let's start with the first one. So what is geometry? Well, there are a couple of different things that one can mean by geometry. So the first one is Euclidean geometry. So this can study lines and curves on a plane or on Rn. And normally we do this up to affine transformation. So we say a triangle, it's equivalent to a slightly bigger triangle where you scale it, or to the same triangle if you rotate it. Another thing that we can mean by geometry is Riemannian or differential geometry. So here the point is that locally, if you pick a point and you look at a neighborhood around it, it should look like the first case. So even really just Rn, not even something inside of Rn. But the interesting point is that we glue those points together in a more interesting way. And when we say this word glue, we have to sort of specify how we do that. And in differential geometry, we do this using smooth, real valued functions. So for example, here are the couple of objects you could get out of this gluing procedure. One of them is this thing called a Riemann surface. So as a set, it's just the quotient of the complex plane by a lattice. So tau here is some complex number with positive imaginary value, and you just identify points in C such that their difference is an integer plus tau times another integer. And so here I'm sort of explaining this as a quotient, but you could also, the picture sort of makes clear that so it looks like a donut, but every point around the donut, very closely around that point, it looks a little bit like R2, but it's wrapped around in an interesting way. Another example is spheres. So if you take a ball or an end sphere, this is again you're gluing Euclidean spaces together in an interesting way. So let's move on to the second word in the first research interest, which is algebraic. So here we sort of modify the 2 points that I said before. So locally now, what we are going to do is we are going to pick a polynomial. So as an example, let's say it's 3 variables, x, y, and z. F is a polynomial, and we want to look at the zeros of this polynomial. So, which values of x, y, and z, once I plug in, I just get 0. So this is going to be inside of some space, k, and k here could actually be, well, the real numbers, the complex numbers, and we're going to see in a bit, it could also be other fields or other commutative rings. So here are a couple of examples. This is called a nodal cubic. This is just a parabola, right? So all of those live inside, we could either take R2, in which case the picture is exactly what you see, or you could also take C, in which case, there are a couple of dimensions that this picture doesn't quite show. But then the second step, actually, that one has to do to really get interesting geometric objects is to glue. And again, the clue here is like, how do we glue it? But this time around, we glue it using polynomials. The point is because locally as well, we only were using just polynomials. So what are examples? Well, the Riemann surface sigma from before is one example. Maybe I want to explain much more why that's algebraic, but that's a very classical thing. Another example, so the 2 sphere. So topologically, it's the same as the projective space over the complex numbers. Just to recall, another way of saying what this projective space is you take C2, C squared, and you look at the space of lines going through the origin. So that's sort of a description as a set, but how do you get this from this procedure? Well, take C and C. So C is the set of points inside of C where the 0 polynomial is 0. So it's kind of trivially, it looks locally like that. And then you glue it with itself, but you do something interesting. One copy has coordinate Z, and let's say the other copy has coordinate W, and then you send Z to 1 over Z. W is 1 over Z. So in this P1, the idea is that one C is everything except for a point at infinity, and the other C is everything except for the point at 0. And where Z is non-zero, we are gluing those things via this function, which is, when we say like use polynomials to glue here, it's a bit, this function is not really a polynomial, but the idea is it's 1 over polynomial, and that's still okay. The main observation then that was very important to algebraic geometry in the 60s and then led to a big development was due to Grothendieck. So what he said is that one can actually consider all fields, or all, more generally, commutative rings at the same time. So how is one supposed to do that? Well, so suppose we started with f that we had before, which was just a polynomial in kxyz, and then we formed a ring, which is kxyz quotient the ideal generated by f. Let me call this R. And now, if I'm giving any k algebra, so recall this is just a commutative ring with a map from k, then I can take this k algebra and send it to a set of homomorphisms of k algebras from A to this ring that I wrote down. So now, seeing this object as a functor that to any k algebra associates a set, this is the point of view where this ring now becomes a scheme. So it's this geometric object gets this categorical incarnation, if you want, because there's a set that is keeping track of what this object is or what it's doing. And this point of view is very valuable because it allows one to use a lot of powerful machinery that category theory gets you to study those kinds of objects, and also to the freedom of moving between commutative rings allows one to, if one wants to prove something for a specific commutative ring, sometimes it's easier to prove it for some other rings and then understand what happens when you come to the one that you are actually interested in. And yeah, a lot of our algebraic geometry revolves around this kind of ideas. So one remark here is that, so I talked about the functor, so it goes from this category to this category. So I just want to say that this category on the left, there's a different description of it. So I can look at polynomial k algebras. So those are just things that look like k, x1, x2, up to x to the n. Take the opposite category and then look at functors from this into sets. And it's an exercise you can do that functors from this category to that, which preserves finite products, recover all the k algebras. So in a sense, try to understand an arbitrary k algebra is the same thing as understanding what it does to polynomial k algebras via like an embedding like this, formally speaking, via the unit embedding. And the category on the right, I'll just trivially rephrase and say sets are just functors from points to a set. But it's going to be clear why I'm doing this in a second. So now we got finally to the last word, so derived. What does the derived mean? Well, so the main motivation comes from algebraic topology, where I should say there are many motivations, but I want to mention the one from algebraic topology. So in algebraic topology, if you're given a topological space, you can try to study its cohomology and understand some stuff about the space. But actually, it's better if you stay with the cochains of the space. In other words, when you pass to the cohomology, there's some structure here that you're killing. And these cochains, up to an appropriate notion of equivalence, they know more things about the space. So for example, they can tell if your space was an iterated loop space. So if actually was actually homotopy equivalent to the nth loops on some other space Y. They can also understand the rational homotopy type via rational homotopy theory and many other things. So the point is this object is somehow more like contains more information. And normally this object it goes by a different name. So one of them is a commutative differential graded algebra. So I could just fill out what the definition of that is, but let me try to not do that and just give you a conceptual way of thinking about how you would get to that. So one way to think about this is that this should all happen in some higher category context. So the idea is that we should pass from one categories to infinity categories. So the objects that were spaces should be substituted by topological spaces up to homotopy equivalence, or chain complexes if you prefer in this picture, chain cochains. And so the definition of what the derived algebras would be is, well, we just copy the formula we had before, except we substitute sets for spaces, right? So SPC just means spaces. And here, those functors should be interpreted appropriately. So they should be interpreted as functors of infinity categories. But just to say, this category on the left, it's still just an ordinary category, just thought as an infinity category. And then the category on the right, which sets, now just becomes functors from points to spaces, which is again just spaces. And then finally, what a derived scheme is just a functor from derived K algebras into spaces. And the thing that I don't have time to get into details is that most of the functors that show up via that procedure I showed you before satisfy some property. So really, that functor that I showed you before, spec R. I'll backtrack. So this functor is really encoding just this very first idea, and then one also can put anything that looks like this as a functor. But then the question that remains is that there's still more functors here than things that you get from putting 1 and 2 together. So how do you describe exactly the ones that you get from 1 and 2 together? So that's that's where the satisfying some properties comes from. What is theory? Well, really there's an implicit group here. So it's related to the study of groups. So suppose G is a group. Groups are very ubiquitous in mathematics. They keep track of symmetries, right? And they come in many flavors. So let me just list a couple of them. So one is G could be a finite set with the structure of a group. So an example is the group of permutations of n elements. G could be a smooth manifold with the structure of a group. Those are also known as Lie groups. So an example, the special linear group, two variables, or the special orthogonal group. And G could be an algebraic variety. So the kind of objects that we study in algebraic geometry with also the structure of a group. So examples would be general linear group on a field of finitely many elements, say P, or special linear group on QP, or a bunch of other groups, or even special linear group just overlaying the integers. The question we want to ask here is, how do we understand G? Well, the answer really depends on what do you mean. Here's one thing you could do. You could want to classify all of the groups, figure out what are all the groups that exist out there. So in this case, let me quickly go through what some of the answers look like. For the second case, you can classify at least all compact Lie groups. And this is done by thinking diagrams. It's a very beautiful story. Another situation, for instance, the third one, if you want to classify all reductive algebraic groups, that can also be done in a sort of very interesting combinatorial way. So to talk about root systems, it's given by a pair of lattices, so R and R check, and then vectors in those lattices, and the check here means that there's a pairing between those two guys. Or you could also try to classify all finite groups. Well, that becomes a very hard question. When you restrict this notion of simple finite groups, it was a monumental work throughout the 80s by a lot of people to classify them. Another way you could try to answer this question is, how can we understand groups in nature? To make it more precise, it's like, how do they act on other mathematical objects we care about? Because at the end of the day, groups somehow keep track of symmetries, and once they act on something, they're witnessing a symmetry that object has. And maybe that's actually more interesting than understanding what are all the groups. The first thing you could say is, like, suppose we have this group G and it's acting on S, which is just a set. Well, here we run into this problem that there's not much structure in a set. So we actually don't get much from this idea. What if we were to substitute S by a vector space and have G acting on B? Now, actually, things start to get more interesting. And this is the point where the word representation comes in. So this is what representation theory is. Let's refine our second question of understanding groups in nature and try to understand the following. How can we understand all representations of a given group or classify them all? Turns out that that's lots of work. First of all, the flavors multiply because once you have a group and now a vector space, so the vector space could be over some other field. So you can vary the field here and you can vary the group there. So there are different flavors of representation theory depending on what you pick. And for some of those, there's still many open questions. And just to give you an idea, this group that's very easy to write down, special linear group. over R. So 2 by 2 matrices with determinant is equal to 1. If you want to understand all of its irreducible representations, so this word here just means any representation that you can sort of split as a direct sum of two smaller. There's a big list. You get finite dimensional representations, you get discrete series, limits of those, principal series, fit together in an interesting way, and the ways you recover them depends on a couple of parameters. So these have discrete parameters, these have continuous parameters. So one of the smallest matrix groups you can imagine, suppose you were looking at 10 by 10 matrices and you wanted to do those things, it can quickly become a little bit out of hand. So how can you have all of that information packaged in a more comprehensible way? One answer is to use geometry. In this example of SL2R, all of the things I showed you up above, they actually show up as solutions to systems, partial differential equations with symmetries. Those are also known by the name of D modules. In our example, from R, we have to pass to C, but we still consider SL2C, and then we take the quotient by a special subgroup. So this is called the Borel subgroup. The explicit description is just the group of upper triangular matrices. And once you look at this quotient, this is actually isomorphic to the projected space over C. And there's still some other action here by the special orthogonal group. All of those things show up as solving partial differential equations, but that they live in space. You can compress all of that information in something that's a bit easier to visualize. So the main point is that the geometry of spaces, which are constructed actually out of G, can be used to systematically construct vector spaces where G actually acts. So that's the geometric part of representation theory. We can actually do even more with geometry. So here's another example, very interesting. Mentioned that classifying groups could be an interesting question. And for reductive algebraic groups, this is given by this data. There's a Z mod to Z symmetry. You could swap those things, and this is still satisfies the axioms that we require this to satisfy. You could ask, what is the group that comes out of this? And you have to go for this whole theory of classification. It's not that easy to write down what it is. And if you knew this one that you started with, you could ask, is there a more direct way to go between that? And the answer is yes, via geometry. So here, double brackets T means that if these were, say, 2 by 2 matrices with coefficients in C, here we consider 2 by 2 matrices with coefficients in Lohan series in C. And then we take the quotient of the space by the same thing, but with double brackets, the Taylor series. If we were to look at some kind of partial differential equations on the space with some symmetry, essentially the geometry or the topology of the space, it knows everything about this group. It can recover this group, it can recover its finite dimensional representations, and actually much more. Finally, I just want to mention some questions and applications which are related to those two research areas that I tried to give you an idea of. In this area, a lot of questions are related to first developing the basics of the theory that has taken a lot of work by a lot of people, and trying to understand analogs of classical algebra geometric constructions. So what are quasi-coherent sheets in this context? How do they talk about the Tau cohomology? Lots of aspects of projected geometry are also still to be worked out. Second point, again in derived algebraic geometry, is the question of representability. If you were given a functor from derived rings into spaces, how do you tell if this was glued from derived affine schemes? And there are many applications to this kind of to understanding this question. One of them is to construct moduli spaces. A notable application was the construction of topological modular forms. The third question is derived algebraic geometry is especially suited to treat questions related to deformation theory. If you never heard about deformation theory, roughly the idea is if you have some space with some extra structure, maybe it has a complex structure, because that extra structure, in this case, let's say complex structure, so there's an object that parametrizes it. Maybe there are different choices for this extra structure. Then you could ask, can I actually construct a bigger space over this space that parametrizes all those structures, such that if I look at the fiber at a specific point, I recover the one that I have, but it actually knows about how to vary those things. A lot of natural questions in classical algebraic geometry fall into this helm of deformation theory, and derived algebraic geometry is especially well suited to answer those questions. Another application and many questions related to this is to extend usual constructions to other geometric objects that derived algebraic geometry allows you to do. So one example I want to give you is the study of symplectic geometry. So normally, if you have, let's say, an algebraic variety, to be symplectic is roughly to say that you have an isomorphism between a tangent and a cotangent space. Now, suppose you were to look at a space that's a little bit different. Consider the space which is a point modulo by group. So this is stack. You don't exactly need to know what the definition is, but a little computation tells you that the tangent space looks like the Lie algebra shifted. So this is cohomological degree -1. The cotangent space actually looks like the dual of the Lie algebra, but now in cohomological degree 1. Sometimes by taking some extra data on the group, like by linear pairing, we can identify those two things. The Lie algebra is dual, but there's still this shift that doesn't allow you to do this on the nodes. But if you allow yourself to understand this as this derived object, so this is not just a vector space anymore, a vector bundle, but it's really complex of such, then you could do things like shift. So the shift that was already there to start with. And then you can ask, maybe after a shift, I still have this isomorphism. And this gives this very simple idea, actually. Gives a whole different flavor of symplectic geometry. It's called shifted symplectic geometry, and has had many applications, especially to actually representation theory. Another big question in my area that somehow uses both of the things that I've talked about before is the geometric length program or program. So this again comes in many flavors. First one depends on which group you pick. If your group has complex coefficients, it's called geometric. If it has QP coefficients, it's sometimes called local. And if it has a number field, let's say just Q, it's called the global. And normally there are two sides in the story. So in one side, which is called automorphic, there's a lot of the geometry of G. And on the other side, called spectral, there's the geometry of G-check, but really here we should say more the representation of G-check. And another thing that, a lot of the technical machinery that went into developing derived algebraic geometry allows you to do now is to look at groups acting in other things. So, for example, in categories as well, not just in vector spaces. And that has led to many interesting developments. Maybe I'll mention two more quick applications. So another application of geometric representation theory is in the theory of what's called character sheaves. What is a character? It's a function on a group that normally comes in the following way. If you were to have a representation and you were to take the trace of the matrices, then you get a function on G that's invariant for the conjugation action by G. And those functions can know a lot about the representation theory of G, but to construct them sometimes can be a bit complicated because again, you might have to construct all those representations and take the trace. The thing that the geometry buys you is some sort of shortcut to construct those functions. And another application of those two areas roughly put together, which is, as I mentioned before, geometric representation theory sometimes allows us to understand things about classifications of groups. So here the statement of the geometric Satake says that if you look at reverse sheaves on this object on the right, it recovers the category of finite dimensional representations of G-check. But this is at the level of a billion categories. You could ask, can we lift this into derived categories or infinity categories? And the answer is yes, one can. If on the right, we were to consider the derived categories of sheaves. But on the left, we have to move away from this object and consider something a little bit involved. So, there's a couple of stacks here, and then we take this fiber product between them. But the thing that's actually important is this fiber product, which one should think as just the intersection of those two things. It shouldn't be thought in the usual way of algebraic geometry. This should be taken as a derived fiber product that you could actually get the correct answer. It's another instance where usual constructions in algebraic geometry somehow take you outside of algebraic geometry into derived algebraic geometry if you actually want to get the right answer. Okay, I think this is all I have to say. Thank you so much for your attention.